Nach 2 January und auch 2 January rauchen.
Before I start deducting these problems, do you have any questions about last time, about any organizational issues? I received an email about next week. So next week there's this tutorial with Yele, where you get to see the solutions of the third assignment, which is also a mock exam. And someone that is studying public economics told me that it's not a good time to have the tutorial because it's at the same time with something else that public econ people have to attend. Is that true?
What time?
When is it starting? Thursday.
It's on Thursday between 4 and 6.
Yeah.
4 European.
Yeah.
I need to ask Liana first because I don't know when he's available. But if we move it 2 hours before, do you have something else?
No.
Yes? No? Okay. I will try to sort it out with him, and I will try to find a room, and I will let you know on Blackboard how it goes. I will try my best, but I don't know if it's going to work out. Okay? Okay, so now that's done, and you also know that the third assignment is online and is due next week Wednesday. Perfect. Okay. So, the sixth problem, it's about the real business cycle model. Essentially, the real business cycle model is very similar to what we have been doing so far. It has a representative household that's maximizing their lifetime utility. They're choosing their consumption, they're choosing their hours worked, they're choosing their savings. But this time, what changes is we introduce technology. So there is this technology factor that we use in order to produce goods and services. And now that technology is stochastic, which means that in the next period there might be a technology shock, for example, say a supply chain disruption, that makes the technology less productive, and therefore the economy less productive, and therefore consumption, investment, etc. will fall. Okay? And because of this stochasticity in technology, then the household has to consider all of these different states that they might find themselves in the upcoming periods. Okay? So now they're not just maximizing utility anymore, they're maximizing their expected utility, given the fact they might face shocks in some states. Okay? So let me write down the problem. This problem is this. Okay, this is the household side. And what the maximization problem is similar to before. Right now we have this expectation operator. And then the sum of utilities as we know. They're choosing their consumption, they're choosing their hours worked, and they're choosing also their capital. And they also have the same budget constraint as before. And then there's another budget constraint, which defines how capital is achieved. Okay, this is the household side. Is anyone confused about the expectations operator? Like why it's there, what it denotes? Or is it okay? Have you talked about it in the lecture? It's not okay. So what this expectation operator tells you is that what this expectations operator tells you is that at time t is equal to 0, you have to maximize your expected utility. And what does expected utility mean? It means that these are, by the way, these dots, they are states of the world that you might end up in. Say this is employed and in a recession, this is unemployed in a recession, and this is employed in a boom, etc., etc. Okay? So what you do is you say, okay, I am in this state of the world. And I know that there's some probabilities that in the future there will be a recession and I will be unemployed, and there will be a recession and I will be employed. Okay? So what this expectation operator tells you is that I consider all of the states that I might end up in at time 0. And therefore, when I make my choices about consumption or hours worked or whatever, I have to consider that I will not be employed forever, there will not be good time, economic times forever, and you assign in this expectations operator some probabilities to the states that are implicitly there by the expectations operator. Okay? This is all it says. For all you care, you can just ignore it and just put it around when you're deriving your solutions. It just says that at time t, I'm not sure what, for example, capital t plus 1 will be, because there might be a technology shock, which I'm not aware of. Therefore, everything that might happen at t plus 1, or t is equal to 1 here, will take an expectations operator. So at time t, capital will be equal to kt, and at time t, kt plus 1 will be the expectation of that capital, which can be either here or here. And to denote that uncertainty, we just use the expectations operator. Okay? It's just a way of saying there's different states in the world, and when I make my economic decisions, I'm aware of the states, and I assign them probabilities. But for the math, it doesn't matter that much. Okay, so exercise 8. I have to derive the Euler equation and the optimal labor supply, as we've done so far many times. So there is 2 budget constraints. So I will start before writing my Lagrangian by merging these budget constraints. And I will do so by putting IT by rearranging the second budget constraint and plugging in for IT. This will give me my new budget constraint. expectations operator in front of kt plus 1. Yes. Okay, just click the signs. I think there must be a typo that in the solution. Okay. But my question, why is it expectation of kt plus 1 and not just kt plus 1? Okay. Remember we said that we're solving our model and the optimality conditions have to hold in every period. And I'm solving this at time t. And I know that I have to choose a capital for the next period. But I don't know the exact value of that capital. It could be 5, it could be 6, given the productivity of the state, which is random. Therefore, I will choose the expectation of that capital. Does that make sense? I cannot choose 5 or 6 because I don't know where I will end up. So I will take some sort of expected value of what's going to happen, and I will work with that. Okay? So every time you're in t, all the variables in t plus 1, t plus 2, etc. will take an expectations operator. Does that make sense? Okay. So let me write down my Lagrangian now, which essentially is the same as before, it just has this expectations operator now. Now I have my Lagrangian, and I will remember they're choosing ours. Oh yeah, good question. Yes.
Why are we dropping the expectation operator here with kt plus?
Since they're-
moving it.
yeah.
What's the sign next to the lambda? Is it lambda 0? No, lambda t.
Lambda
right?
t.
Oh, okay, yeah.
Okay. So remember, they're choosing consumption today. They're choosing capital tomorrow, and they're choosing hours work today. So there will be 3 first order conditions. Let's start with consumption. I'll rearrange it so it's like this, so we can plug it in later. Let's also do capital t plus 1. So capital t plus 1 shows up here, right? And then it will show up also in the next period, in the budget constraint again, as we've done before, okay? And then remember, because I am choosing capital that is gonna be available in the next period, now I need an expectations operator, okay? Because I'm choosing a time t, my capital for the next period, which I'm not sure about. So I need an expectations operator. lambda t is at the other side. Why do I have an expectations operator here, not here? In order to help you, where does each derivative come from? Where does lambda t come from, and where does the thing in the expectations operator come from? Okay, so lambda t comes from here, right? Right? Okay, what is this? What is this kt plus 1 in that side of the boundary constraint? Where did I get this kt plus 1 from? Did it fall from the sky, or? So it's something that I came to this period with, right? I chose it next period, the previous period. And I'm carrying it with me. So today it's predetermined. And what I'm choosing in the next period will get the expectations operator, because this part, it will show up in the sum if you expand the sum in the next period. Okay? Does that make sense? Probably not. Okay, let me write out the sum. We wrote down also a few tutorials. So, in this period, what do I know? I know how much consumption I want to choose. I know how much hours work I want to choose. These things I know. I don't form any expectations about them. I choose them. And I also know how much capital I will choose. This is my decision. I'm making this decision. So if I say this is my capital, but I choose this period, time t, it's going to be 5. That's for sure. There's no expectation about that. Okay? Where the expectation comes in is here. Because here, I don't know how productive my capital will be in the next period. Okay? general one. Now that we were talking about.
I think it's the same on your notes that RT area equation.
Okay, I'll change it now, but it's just a definition. It's just a convention. But does it make sense why I use the expectations operator for the next period? Okay. The expectations operator only comes up if you're using capital. So if you're using consumption and hours worked, you can ignore it. Okay? You just take it here and then keep it like that and forget about it. Yeah.
And just for the notation, the expectation operator, is it EO or E0?
For the Lagrangian, it's E0.
Okay.
For the optimality conditions, CT.
Okay.
Because for the optimality conditions, we say that it needs to hold in each period
Yes.
for the information set I have in each period, in each state. Okay, here was the mistake, right? Here. Hey. Okay. This is equation 1. This is equation 2. And then the last one is the first order condition with respect to hours work. Again, there is no expectations operator here because I only choose this period. And for this period, I am certain. Guys, I apologize. I think some of the signs are wrong. So I will look at it again. The optimality conditions, the way they are written, rearranged, they are fine. But some of the signs are wrong. So I will look at it again and correct the solution, okay? So if you have trouble with the signs right now, just ignore them. Okay? And this is equation the automatic conditions are fine. So equation 3, 2, and 1 are fine. There was a hand somewhere?
Could you explain again when we derive for kt plus 1, why we don't have E0 minus beta t lambda t?
And why it's ET?
No.
Why there's no expectations operator?
Yeah, before
That's-
minus beta t and lambda t.
Yeah. Because it's here. You're in this. So each of these optimality conditions holds at time t, and in the state you're in. And you know the state you're in. So at time t, you don't have to form any expectations. You know your state and you know your time. But for the next period, for t plus 1, you don't know where you're going to end up. You might end up unemployed, you might end up in a recession, you might end up in a very good economic environment. That's why if it comes from the part of the Lagrangian that is at time t, you don't need any expectations. If it comes for the part that is at t plus 1, there you need to form expectations.
Okay, I see.
Yeah.
Thank you.
Okay, so to derive the Euler equation, plus 1. Okay, this is the other equation. Notice that my CT plus 1 is inside the expectations because it's for the next period. Okay? And I don't know how much my consumption will be for sure because there might be a productivity shortage. Okay? Okay. We derive the labor supply. Labor supply. And this is the optimal labor. You see the conditions are the same like in the previous problem sets. The only difference is this expectations operator because of the randomness and productivity. But the optimal conditions, they're the same. Any questions so far? Yeah.
What is the exponent on the labor of the energy?
It's this phi.
Phi.
Yeah.
What is it looking like?
It represents. Can I postpone it for the next exercise? Because I'm going to talk about it. Okay. So, exercise B. Calculate the fridge elasticity. Okay. Do you have you talked about the fridge elasticity in the lecture? Okay. No. Okay. So the definition of the fridge elasticity in math will be this. Okay. This is say xi. So economists, when they pick elasticity for some reason, they like to name them with Greek letters. So just to mention, you can call it whatever you want. But this is the fridge elasticity. And the definition of it in math terms is this. Okay? This is just how you define elasticities in any sort of economic context. And what the fridge elasticity does, it measures how responsive hours worked are to changes in wage. And what it also does, it holds your marginal utility of wealth constant. So in this way, if you have any wage changes, the fridge elasticity abstracts from any income effects. It just measures purely the substitution effect. So if my wage increases, how much I will choose to work more, because now not working as much becomes expensive, right? The income effect would say, yeah, but now if my wage is higher, I'm also richer overall, right? So maybe I could afford to work less. But this fridge elasticity, it removes that part. So it tells you purely how much more would you work if your wage would increase. Okay? Let me write it down. Measures responsive hours worked are to changes in the wage given constant marginal utility of all. So your so the income effect does not matter to you. Abstract. So in order to calculate this elasticity, I need some sort of expression with NT and WT, which is my. So I will take the optimal labor supply for that. Okay? Use optimal labor supply. Okay? I will rearrange it a bit because it will be easier for when we take derivative. I'm sorry for the bad handwriting. Okay. And now what do I need? I need this derivative there. Change in NT given the change of WT. Yeah.
Sorry, what is the two words after given?
Given constant marginal utility of wealth. Yeah. Okay. Now, what is the derivative of this with respect to the with respect to the wage? So it's gonna be 1 over f. This. Reduce the exponent by 1, and then you also need the inner derivative using the product rule. Okay? This can be rewritten as 1 over f. So basically what I'm going to do, I'm just going to split this part, this ratio, into 2 exponents. Okay? So I'm going to do times minus 1, and this 1 over ct stays the same. Okay. Use that nt is equal to wt over ct raised to the power of 1 minus 5. So I'm going to replace this term here with nt. Wt. I just flipped this for clarity. And then times 1 over ct, these are cancelled out. So what I have is 1 over f times nt. Okay, this is the first part of my elasticity, so it's the derivative. I still need to multiply it with this for the elasticity. So the elasticity is then given by 1 over f times this. This is just the definition of the elasticity. I just plugged in for the derivative and then multiplied it with the second part. Okay. This is the inverse of this, it cancels out. So what remains is 1 over 5. And now the phi is, what it does is it measures the disutility of labor. So if you have a high phi, it's a parameter, if you have a high phi, your disutility rises very fast the more you work. Okay? So the household dislikes working more, even for higher wages. So what it will do, you see they're inversely related. So if phi increases, the elasticity will decrease, which means that for for given wages, the hours worked will change less, okay? Which means that the labor supply is quite rigid. It will not respond much to wage changes, okay? And it's just the parameter, this phi that we use to calibrate our model. It comes from the literature usually, because you want to match the response of hours worked in the data in a recession, okay? Let me write this down, so I5 means that this utility rises fast from working more.
Das ist auch ein Fee. Ja, weil das ist Schreibschriftfee, was anderes.
The household
Ja, wirklich.
is like
Das bringt mit an.
working more for a given wage change.
Habe ich das jetzt?
So, fridge elasticity is lower, so hours work change less, and labor supply is rigid. Okay? Yes.
Is there a reason that we denote phi one time differently than the other? So,
It's the same.
okay.
By the way, I'm Greek, so if I do this, I'm allowed.
I just wanted to say that there's an additional phi in the solution.
I updated the solutions this morning, so I think have the old version.
Okay.
Okay? So,
Ah,
yeah, I updated the solutions and then I made some things worse, so I will update them again, but whatever I'm writing here is correct.
okay.
Yeah.
So
Phi.
it's the same as the circle.
Yeah, sorry, yeah, it's the same. It's just sometimes it's like easier to do this, but yeah, okay. I will try to stick to one phi. Okay. So any questions about the fridge elasticity and how it relates to phi and how it relates to the model? Yeah.
So that letter is Xi, right?
Yes, it's exact. Yes.
Could you explain to the power of f again, please?
The power of f.
Yeah, the Frisch elasticity, the sign, the Greek symbol.
Yes.
It's there's an F and a T.
Yeah.
You know what I mean?
No.
I think the F means fresh.
Ah.
Yeah.
that
Sorry,
makes
it's
sense.
for fridge. Yeah.
Okay.
Yeah.
Yes, that.
Yeah. Thanks for clarifying. Okay. So that's it. Okay. So now we have the firm side again. We're just gonna derive the firm's labor and capital demand, like we did a lot of times before. It's the same. But I will do it for completeness. So again, the firm, there's a representative firm that maximizes profits and demands labor and capital from the household. And for that, they will pay a wage and they will pay an interest rate. Maximum T. And these are the profits of the firm. Notice that the productivity shows up here for the first time. So essentially, we're saying that whatever productivity shock happens, it affects how we produce given capital and labor. So it affects our output, and therefore it will affect our resources overall, it will affect our consume less if there's a bad productivity state. We'll also be able to save less. Okay? And it all starts happening here. First order condition with respect to KT. This is the same as before. Now I started being sloppy with big letters and capital letters. Okay, let me just write this for completeness. These big letters. Okay. KT, -1, LT1. This is the same as before, just for labor this time. One minus alpha, AT. This is the same as in the previous problem. I'm just deriving this because they will help us when we log linearize the optimality conditions. Because we can plug in them for RT and WT. Okay? And now comes the log linearization. We have to log linearize the order equation, the optimal labor supply, the budget constraint, and the technology process. Okay? And it says, as a hint, we can insert the firm's labor demand, capital demand, production function, the budget constraint before the log linearization. So essentially, what we will do is whatever we derived there for RT and WT, we will plug them in because then we will have less variables to work with. Okay? So, let's start with the technology process, which is easy. Silent T. So, what kind of process is this? Maybe from your time series classes or geometry? So it's an AR1 process. It means that the value today depends partly on the value yesterday, and there's also some randomness to it. This epsilon t is random, and this will be essentially these shocks, these productivity shocks we will face. Yes?
Is this a row or a P in front of the log?
Sorry?
Is this in front of the log? Is it a row or a P?
It's a row. Okay, it's an AR1 process, and it shows persistence, which means if there's a shock, it will propagate. It will not just happen today and then disappear, because you see, if there's a shock today, this will increase technology today or decrease. And then next period's technology, since it depends on this period's technology, it will carry a bit of the shock with them. And how much this shock will stay in the system, it depends on how persistent this process is. So what this rho is. If it's close to 1, it's very persistent. So if a shock happens, we will never, if it's 1, we will never go back to the same state again. Yeah?
Shouldn't it be 80 plus 1?
Here?
No, there.
No. Depends on the past. So this is an AR1 process. And the AR1 processes, they depend on their history, they depend on their past. Okay. So, yeah, I need to log linearize this. How do I do this? Like, what is, from all the things we did last time, what would be the best approach? Gloria?
Nah, much Christmas.
Okay. But essentially, I told you, if you have logs, the good thing is that if you have logs already, you can just use the first method, which was to subtract the log steady state of something. Okay? So now, I will write down the steady state of this in logs. Okay? Use steady state in logs. So it will be log of a bar plus rho of log of a bar plus epsilon a bar. Okay? Then I will subtract this steady state in log. From both sides. Okay, this is side 1, and this is the right hand side. Okay? What is this definition here? So it's the definition of a variable in log deviations from its steady state. It's this thing that we wrote last time, this small at hat. Okay? So the goal of this exercise is to remember last time, or like the last tutorial, we were writing everything down in deviations from their steady state. And this is the goal of the exercise. Everything we derived so far, we want to write them in deviations from their steady state. And we said there's two methods to do this. Either you do the method with the logs. If you have a product, if you have a function that is a product without any addition or multiplication. Here there is an addition multiplication, but it's already in logs. Okay? So you can just take the first approach and subtract the steady state. And we said if we have addition or multiplication, then we need to do the Taylor. Sorry, if we have addition or subtraction, then we need to do the Taylor approximation. And we will do this for all of the equations that are given to us. Okay? Okay. This is okay, and this is the same. Here. And then, so this shows there. Okay, so it's given in the exercise that the productivity shock, so this epsilon, is IID, so it's independent, identically and independently distributed, and has a mean of 0. So its steady state is 0. Okay, it's given in the exercise. Okay, so this is what's left when we log linear essays. This is the technology process. Let's go on with the optimal labor supply. So this is equation. It's a product, right? So what would be your approach to solving this? How would you solve it from the two methods that you know? Yep. No. So if it's a product, just take the logs because it's much easier. Because Taylor, you will have to do the derivatives. You will have to expand by the ratios of the steady state to find the deviations. If you have something like this that doesn't have addition or subtraction, just take the logs and it's going to be easy. Okay? So, first of all, I want to get rid of this WT. first use that WT is equal to 1 over alpha, sorry, 1 minus alpha, AT, KT, NT, minus alpha, mathematic condition. I know you're gonna tell me why are you gonna add more variables here, but essentially it will help us with the rest of the exercises because at some point we will have to reduce everything into a system of 3 variables, which is KT, NT, and consumption. So if we do it now, it's easier than doing it later. Okay? So the optimal labor supply then becomes this. Okay, step 1. Take load. This will be the log of 1 minus alpha plus the log of AT plus the log of KT minus the log of AT equal to 5 log NT plus log of CT. Okay? Step 2. What was step 2 from last time? Yeah.
Extract the log sensation.
Thank you. So it would be log steady state equal to 1 minus alpha stays the same because it's just a constant. It's steady state is itself. And then step 3 is the subtraction. Okay, so it's gonna be what's 21? Minus log of 1 minus alpha, this will be here, plus log of AT, log of AT, minus log of 8, plus A log AT, minus A log A bar, plus log of NT, because here there's a minus, so if I subtract it, it's gonna be plus. Okay. And then it's equal to 5 log of NT minus 5 log of N plus log of CT minus log C bar. Okay, and now I just apply the definition. This cancels out. This is the definition of this little AT hat. This, if you factor out alpha, it's the definition of a small KT hat, etc., etc. Okay? And then I can rearrange this so that empty hat is at the other side. Okay, it's just algebra. Okay.
conclusion at the end. You added, yeah, right. Why is that not minus the log steady state of layer supply?
It is answer. Thank you. The rest should be fine. Thank you. Okay. Let's do the other equation. It's gonna be a bit painful. So essentially the order equation is one of the most complicated things you can look linear at. So if you manage this, don't worry, then you're fine. Because it doesn't get much worse than this, okay? Because it has a bunch of variables, it has expectations, you need to do a little trick. So we will do this. Just try to follow through and have a look at home how we did it. And if you can replicate and understand this, you're gonna be fine, okay? Well, it's written like okay. First of all, as instructed, plug in for RT. This was given to us in the exercise, so we have to do this. And I got this from the firm maximization problem, okay? I'm just plugging in here, I'm not doing it. Okay, so I think it's clear that we cannot take the most of this. So we have to do the Taylor approximation. Does anyone remember how we did the Taylor approximation? What the general steps were? Okay. So remember we said we have this Taylor approximation. What we're gonna do is we're gonna write down. We're not gonna touch this side. We said we don't touch this side at the beginning. And then what we do is we write down first of all the steady state of something, and then we write down the derivatives with respect to all of the variables we have. This would be Ct plus 1, At plus 1, Kt plus 1, and Nt plus 1. So you need 4 derivatives. And then you will evaluate those derivatives at the steady state. And then you will multiply with the variable with which you respect your taking the derivative to, minus its steady state. Okay? Okay. Use Taylor approximation. We're going to do this step by step. It's okay if it takes a bit longer. Because the rest, once you have the derivatives, the rest is just algebra. Okay. We said we don't touch this side, just forget about it. And then, I need first of all the steady state of this. What is the steady state of this? Yep.
Theta times 1 over C bar. Alpha A bar, K bar alpha minus 1, N bar 1 minus alpha plus 1 minus that.
And why is there no expectations operator?
I'm sorry, come again.
Huh?
I'm sorry, come again.
Why is there no expectations operator?
Because it's a steady state.
In the steady state, there's no shocks. Everything is certain. Okay? If you have a steady state like this, where there's no time indices, you can remove the expectations operator. Okay. And then we need to start taking derivatives. Okay? Let's start with respect to Ct plus 1. It's gonna be basically that beta stays the same. And then what's the derivative of that? It's 1 over Ct plus 1 squared. The rest stays the same. And I will evaluate that at the steady state, which means that instead of writing 1 over Ct plus 1 squared, I'm going to write 1 over C bar squared times the rest in the steady state. Okay? This is what we did also last time we were doing the Taylor approximation. You take the derivative, and then you put the steady states of everything. Okay. Sorry, it's a minus because of the exponent, right? Okay. Now what do I need to multiply this with? We said it's the variable with which you're taking the derivative with respect to minus the deviation of the steady state. So it's going to be Ct plus 1 minus C bar. Do I need something there? Besides brackets. Yeah? The expectation operator, yeah. Why? What does it?
Because there's Ct plus 1.
Yes. Okay? So this is the log linearization at time t. This is the equation at time t. Anything that has an index beyond time t, so t plus 1, t plus 2, etc., I don't know what it's going to be. So I need the expectation of that. Okay? So since there is a Ct plus 1, I need the expectation of that. Okay? And that's how it's going to go. It's the same for the rest of them. What changes is just the derivative, which is the minimal change.
Okay.
So let's take the next derivative